Here we have the stator and frame of a single-phase capacitor start, capacitor run induction motor. I've removed the start and run capacitors and also the overload unit. Let's take a look inside the frame and observe the windings of the stator. So the rotor has been removed. The rotor for this particular motor is known as a squirrel cage rotor because this is an induction motor. It requires no brushes. It works on the principle of mutual induction of the magnetic flux in the stator housing here, inducing a voltage and therefore a magnetic field into the rotor bars of the squirrel cage rotor. But in this video I want to concentrate on the windings of the stator. So the winding I want to look at first is this one here. It's a fairly heavy gauge and it goes around to about there, about halfway, and then the other half of the winding for the other poles are down here. So that section there and this section here is what we call the run winding. So that winding is continuously rated and is energized the time that the motor is running. The resistance of that winding is around about 7 ohms when I last measured it. Unfortunately, with just that winding, just the run winding, this motor is not a self-starting motor. So if the shaft was here, if I gave the shaft a flick in this direction, that would be the direction that the motor would actually start to run at. If I had the motor stationary and I flick the shaft this way, the motor would then run in that direction. But that's not very practical as a way of starting the motor. So what we do is we introduce a start winding. And the start winding goes from here around to here, and from there around to there. And you notice that it's completely out of phase with the run winding. So there's the run winding there, and there's the start winding here. Start winding is a smaller cross-sectional area conductor and has a higher resistance than the run winding, and it's short-term rated, which means there's a centrifugal switch in here that open circuits the start winding at about 80% of the full speed to disconnect the power and prevent damage to the winding insulation. The resistance of this start winding is around about 18 ohms. So without the start winding, we just have a sort of a pulsating magnetic field here, and the rotor would just sit there humming and not turn in either direction until we gave it a bit of a flick. But by introducing the start winding, which is out of phase from the run winding, it produces like an out of phase pulse that allows the rotor to give a kick. Once the motor has actually started to move, it then is away. There's no problem at that stage. It's just getting the motor to actually kick off. And that's the pulse from the start winding doing that. Out of phase by using the resistance characteristics being different from the run winding, and this particular one would also have a start capacitor and a run capacitor to improve the starting and running torque. Another thing about this motor is that sometimes the start winding burns out because the centrifugal switch jams, and in a short period of time the quite resistive start winding overheats and burns out the insulation, and then you're back to the same problem that you have to give the motor a bit of a flick to get it to start. With a motor this size being quite cheap, you just throw it away and replace it with a new one. So there is a bit of an overview of the basic capacitor start, capacitor run, single phase induction motor. Thank you for viewing, and hope that this view of the windings makes it just a little bit easier to appreciate the orientation of the run and start windings. See you in the next one.